Today we are going to continue what we started next time, which is atomic physics for IGCSE. Today we are going to talk about a new topic, which is the half-life. What do we mean by the half-life of a radioactive element or radioactive isotope? It is the time taken by the radioactive source to reach half of its original activity. What does this mean? It means, for example, if I have a sample of phosphorus, 4 milligrams of phosphorus. This phosphorus is radioactive isotope. It is unstable. In order to reach stability, it's going to emit beta particle, and so it's going to change into sulfur. So if this nucleus is going to emit beta particle, it won't be phosphorus anymore, it will change into sulfur. After a while, I might find that this nucleus is going to decay as well, change into sulfur and lose its activity and become stable. These two nuclei have decayed, have lost their activity. And then after a while, another nucleus, and so on. These yellow nuclei are not phosphorus anymore. They are sulfur. They are stable nuclei and they have lost their activity. The time taken for half the sample of the phosphorus to lose its activity is called the half-life. But after 14.3 days, I'm going to find that I have only 2 milligrams of phosphorus and 2 milligrams of sulfur that have decayed, خلاص ده decayed phosphorus have lost their activity. They are not active. I have only 2 milligrams of radioactive phosphorus. Then this time taken by the phosphorus to lose half of its original activity, كان عندي 4 milligrams of radioactive phosphorus. Now I have only 2 milligrams of radioactive phosphorus. So the activity is reduced by 50%. The activity is reduced to half its amount. And then this is going to be repeated again. After another 14.3 days, I'll find that only 1 milligram of phosphorus are still radioactive. They will still emit beta particle, and the other half has changed into another new element, which is the sulfur or decayed phosphorus. It has lost its activity. And after 14.3 days, I'm going to find that the phosphorus is only 0.5 milligrams and another 0.5 milligrams of sulfur is found or is added to the sample. Okay? يبقى what is the half-life? Which number من النمبرز اللي موجودة قدامي is the half-life? The 14.3 days. يبقى the half-life is time. It's not the count. It's not the amount of activity. It is the time taken by the radioactive source to reach half of its original activity. After one half-life elapses, the activity reaches half of its original activity. If two half-lives elapse, the activity will become 1/4. If 3 half-lives elapse, then this means that the activity will become 1/8. Every half-life reduces the activity of the remaining amount of radioactive substance to half its amount. Okay? Now, if I want to plot a graph for the activity of the phosphorus or the remaining phosphorus in my sample, at 0 days I had 4 milligrams of phosphorus. After 14.3 days, this is going to become 2 milligrams. After another 14.3 days, يعني 14.3 plus 14.3, 28.6 days, that I have only 1 milligram of remaining phosphorus. After another 14.3 days, يعني 42.9 days from the beginning of the experiment, the activity will become 0.5. This is the remaining phosphorus. After another 14.3 days, يعني after 57.2 days, the activity will become 0.25. يبقى this is the graph for the radioactive decay. This is how it's going to look like. What does this show? It shows the remaining activity, not the decade count. Okay, it shows the remaining activity. طب let's have a look at this example. In a sample of phosphorus 1532 of mass 4 milligram, what is the remaining amount of phosphorus after 57.2 days? طيب, to solve such a question, first of all, I do not want these days. These are meaningless. I want to convert the periods given in my question into number of half-lives. How 57.2 days represent how many half-lives? يبقى 57.2 over 14.3. This is equivalent to 4 half-lives. Okay, what will be the remaining activity after 4 half-lives elapse? I started with a sample containing 4 milligram of phosphorus. 1 half-life معناها that the activity will be divided by 2 أو multiplied by half. The second half-life, it's another half. Third half-life, another half. And the fourth half-life is another half. Mathematically, this is going to be multiplied by half to the power of 4. I'm going to multiply the original count بتاعي by half to the number of half-lives. Here I have 4 half-lives. Okay, يبقى الامount of remaining phosphorus هنا هتبقى قد ايه؟ هتبقى 4 milligrams. Okay, divided by 1 over 16. Okay, يعني 0.25 milligrams of phosphorus are remaining in the sample. طيب, can I now tell what will be the amount of decayed phosphorus? يعني بقية السامبل هيبقى فيها sulfur. What is the amount of remaining sulfur? This is really easy. يبقى ال amount of sulfur remaining أو ال decayed phosphorus that has changed into sulfur is equal to 4 milligrams minus the remaining activity or the radioactive phosphorus that is remaining in my sample. يبقى it will be 3.75 milligrams of sulfur. In the previous example, we did not consider or we subtracted the activity due to the background or we didn't consider it. أخدنا السامبل على طول. طب, if I have a detector like Geiger-Müller tube and I'm going to count the activity of my source, let's have a look of what we are going to do. A source of radiation produces emissions. The detector records 1000 counts per minute at the beginning of the experiment. What are the readings which will be detected after 2 half-lives elapse if you know that the background radiation is 40 counts per minute? In such question, when we are given the background radiation, then we must take into consideration that not all the 1000 counts per minute are going to divide by 2 when 1 half-life passes. Why is that? Because we have a constant value, which is the background radiation, which will not be affected by the half-lives that passes. يبقى first of all, I need to calculate the activity due to the source only. The 1000 counts include the activity due to the source and the background. I need to get rid of the background radiation. يبقى the activity that I have is 960 counts per minute due to the source. This is the amount that is going to be affected by a half-life. طيب, what will be the remaining activity after 2 half-lives? 1 half-life معناها that the activity will be reduced by half. Another half-life يعني it will be reduced again to half, يعني multiplied by half تاني. يعني كأنها half to the power of 2 أو it will reach 1/4 of its activity. 1/4 of its activity يعني هنا هتبقى 240 counts per minute. This is the remaining activity, the number of nuclei which are still radioactive. طيب the third question, what will be the reading of the detector? The Geiger-Müller tube, is it going to read 240 counts per minute? No, it's going to read both the remaining activity of my source اللي هي 240 counts per minute plus the background radiation. يبقى الديتكتور بتاعي هيقرا 280 counts per minute. يبقى I have to consider and take into consideration the background radiation if it's given in my question. It means it wasn't subtracted from the original readings. I have first to subtract the background radiation, calculate the remaining activity, and then add the background radiation one more time. What are the uses of radioactive isotopes? How do we use the alpha and beta and gamma radiation? Are they helpful or they are something harmful and have to be avoided? They have many useful applications. Number one, they are used to control thickness of paper. Let's say if you are in the industry of paper and you want to make paper or foil, for example, and you want to make sure that the thickness of the paper that is coming out of your factory is 0.1 millimeter. How can you check that every single paper coming out has a thickness of 0.1 millimeter? Okay, you start by placing the paper that have the correct thickness. This is the paper that has thickness of 0.1 millimeter. And you are going to bring a source of beta particle. يبقى أنا عندي radioactive source هنا that emits beta particle. And at the other end, I'm going to put Geiger-Müller tube or a detector that is going to detect the amount of counts. طيب. When this paper having thickness 0.1 millimeter was placed between the radioactive source and the Geiger-Müller tube, we found that the reading detected by the detector was 300 counts per minute. If I'm going to place the paper that is coming out of the factory today, I am going to place these papers between the rollers. If I am going to find that the counts have much decreased, for example, the counts are only 100 counts per minute, what does this show about the thickness of paper? It means that paper is too thick. Why do you tell that the paper is too thick? Because it has absorbed many beta particles. It did not allow the beta particles to pass through it. يبقى decrease in counts shows that paper is too thick. Why is that? Because it has absorbed too many beta particles. And vice versa. يعني إيه vice versa? يعني if I am going to find that the counts have reached 500 counts per minute. Too many beta particles have passed from the other side of the paper to reach the Geiger-Müller tube. This means that paper is too thin. يبقى the opposite is right again. Increasing number of counts shows that paper is too thin. يبقى it allowed too many beta particles to pass. Okay? طيب. Now, why do we use beta particle here? Why is beta particle the correct choice for the radiation to be used? If we use the alpha particle, what do you expect to happen? Do you expect any of the alpha particles to reach the Geiger-Müller tube? No, that's right. Why is that? Because most of the radiations are going to be absorbed by all alpha particle will be absorbed by a paper because it doesn't pass through the paper. So there will be no reading detected by the Geiger-Müller tube. What about using gamma particle or gamma rays? if we use gamma radiation at one end and the Geiger-Müller tube at the other end, do you think that the gamma will be affected by changing the thickness of the paper? Well, it is very penetrative, so it's going to penetrate through the paper and there will be no change in reading in case of the gamma. And plus that the gamma command is going to affect the workers and the people in the place around, as it has a very big range. Okay, so the right choice is to use isotopes that emits beta particle. Second use for radioactive isotopes is the usage of radioactive isotopes to detect leakage in pipes. If I have a pipe found under the ground that carries water or oil, okay, and there is a leakage, we never start by breaking and looking for the leakage. This would be the most expensive and the most exhausting thing to be done. We never do this. What do we do instead? We inject we place source of gamma rays in the water that passes through the pipe. Okay, and then we use a detector on the top of the pipe. And in the position where we find increase in number of counts, this means that there is a leakage in this place. So we move the detector all over the place. Let's say that the counts were 500 counts per minute. If suddenly the number of counts reaches 2000 counts per minute, it means that there is a leakage in this position. Of course, the gamma rays is the most suitable for use because it will not be absorbed by the soil. يبقى alpha and beta will be absorbed by the soil and they will not reach the detector. Okay, and so the correct radioactive isotope is the gamma. But in this case, do we use source of gamma rays like sodium-24, one having short or long half-life? What is the correct thing to be done? Short, طبعا. Why do we use short half-life? Because this is a problem that is going to be fixed in few hours, so I don't want a long half-life in order not to contaminate the water خلاص and the underground soil. Okay, but in case of industry here, I prefer source of beta particle having long half-life. يبقى هنا for industry هنا هتبقى long half-life. لكن this is an occasional situation, so I'm going to use source of gamma rays that has short half-life in order to fix the problem, and then the source of the water is free from any radioactive isotopes and it's safe to be used again. Third use is the use of americium, okay, which emits alpha particle in smoke detectors. The americium emits alpha particle. This alpha particle is going to be used in this circuit. The alpha particle will cause ionization of air. Here we have two plates, one of them connected to the negative terminal of a battery and the other one connected to the positive terminal of a battery or power source. When the alpha particle passes, it has a very strong ionizing effect. It will cause the air molecules here to be ionized, causing the negative electrons to be attracted to the positive plate like this, and the positive ions to be attracted to the negative plate, and this causes a current to flow. When the current passes through this relay coil, it is enough to magnetize the relay coil. So the relay coil, when it becomes magnetized, it is going to attract the normally closed switch, iron switch. Type. If we have smoke, if someone is going to place a cigarette here close to this smoke detector, the smoke will absorb the alpha particle. It will stop the alpha particle. When the alpha particle stops, then the current will stop because the air will not be ionized anymore. So I have a gap here. I have an open circuit عندي positive و negative, بس between them there is air. Okay, في بينهم neutral air molecules that will not allow any current to pass through it. So the current will stop, okay, and the iron switch will close, causing circuit 2 to be a closed circuit. The buzzer is on and the lamp, if there is a lamp, is on too. هنا we use alpha particle. Why especially alpha particle? Because this property or this device depends on the ionizing effect of the alpha particle, and as we said before, the alpha particle is the most ionizing type of radiation. The fourth thing, the use of gamma rays for medical purposes. Gamma rays are used to kill cancerous cells by knowing or by using what is known as a gamma knife. If the gamma rays are directed towards any living cell, it's going to kill this cell. So it's used in some types of tumors to kill cancerous cells. It's also used for sterilization of medical equipments. It's used for food canning, and it's used in medical tracers. Medical tracers, what does it mean? It means that if someone has a blockage in the kidney, for example, then we inject a weak source of gamma rays into his body. That is going to flow with the blood. They will be monitored by camera, and the doctors can identify a problem, whether there is blockage, there is leakage, there is any problem, tumor, for example. Okay, and in this case we use source of gamma rays because the gamma is the least ionizing, so it can be injected inside the body. And of course we use source of gamma rays that has short half-life to minimize the time of exposure of the patient to this type of ionizing radiation. When we are using radioactive isotopes, we have to be careful. Why is that? Because alpha is very highly ionizing. If ingested, it might cause cell mutation, it might cause leukemia. It's very dangerous if ingested, if it enters the human body. Okay, the beta and the gamma are going to be blocked by the skin. Okay, the alpha will be blocked by the skin, but the beta and the gamma are able to be more penetrative. They can penetrate. So we have to minimize the time of exposure, because this will be really dangerous if a person is exposed to radiation for a long time. But what are the precautions that can be done to overcome this? طبعا wear goggles, wear protective coats that contains layers of lead, work in groups, use a film badge which shows the level of radiation, never take food where there is radioactive materials, work in groups, use long tweezers or long tongues to keep radioactive material away from the body, especially in alpha عندها very short range in air. These are the safety precautions when using gamma, when dealing with radioactive isotopes. Okay? Now try please to solve this question.